So my name is Tata Narasinga Rao. It is actually Tata Narasinga Rao in my native language Telugu. So I am Director of Advanced Research Center for Powder Metallurgy and New Materials. It is very well known as ARCI. It is a DST research institute. We do a lot of translational material research. And then when I present also, I will show you what are the areas of work, translation research we do in energy sector as well. So today's session is next generation electrolyzer technologies, green hydrogen production perspective of electrolyzer manufacturers. So we have a bunch of people, very eminent speakers, and without delaying, let us start with the first speaker. I hope Mr. Sridhar Dharmarajan is there here. No? No. So maybe he will join later. Then myself, I have to present. So shall I go ahead and do that in the order? Yeah, right. So once again, welcome and thank you, the organizers, for giving me this opportunity. And you can see International Advanced Research Center for Powder Metallurgy and New Materials is well known as ARCI, and it is a DST institute for autonomous body in Hyderabad. I'm sorry, when I was typing the electrolyzers, it got next to India, so just ignore that one. I just saw this one now. And the mandate and focus for ARCI from Government of India is that in the bottom line, you can see transforming laboratory research into technology and transfer to industry. Next slide, please. So just before I start, I just want to give a very brief introduction. In India, Indian scenario, if you see, we have academia and we have industry. Both are at two sides, and then the arrow shows the technology readiness levels. And then, although we are improving, but in general, we do a lot of excellent research, and then we are actually number third in publications, research publications with very good impact factor and citations. And we keep publishing, and if you see the patent portfolio, we are not doing so well in comparison to our neighboring country, China, and any other developing countries. And on the other hand, the other side, high technology readiness level, where you have system demonstration and near to commercialization, that is the private sectors. A lot of companies are here. I hope you will agree with me that because there is a lot of gap between the academia and industry, industries keep getting components imported and they make the systems and then sell it. And that makes a big difference in the cost, and then, for example, and also compromise on the quality if you are looking for low cost. A simple example is battery packs, what are used for electric vehicles. If you see in last few months, a lot of scooters, especially two-wheelers, three-wheelers, they got blasted at several places in India because the cells, basic cells were imported at very low cost, which are very compromised, and they make just only a battery pack suitable for the scooter, whether it is a 1.5 kilowatt or 2 kilowatt and so on, even auto rickshaws. So now, of course, under my chairmanship, we just made some amendments to A156, and now the stringent amendments are making that the companies have to comply with those amendments. Now what we do, can you just click once more there? So ARCI's role is to bridge the gap. And then I'm not going to give examples because my original lecture is mostly on battery materials because I work on lithium-ion battery materials. But today's one is that it is more hydrogen energy related, and I'm going to talk what we do with electrolyzers, PM, fuel cells, and SOEC. So can you go to next slide? Next slide. So if you come to ARCI, you will see the expert areas. Each box is a center of excellence at ARCI, and all are relevant to the component development and the system development, where all these areas are very important. Where is the powder metallurgy, where you want to make component. For example, we are making bipolar plates, chromium-based interconnects for SOEC with H2E. And surface engineering, a lot of coatings you require, whether if you want to stop hydrogen embrittlement, when you transfer hydrogen, pure hydrogen to metallic pipes, you need to have a proper coatings to avoid hydrogen diffusion into metals. And laser processing, wherever you want to have melting, laser welding, melting or drilling, or so a lot of activities, and additive manufacture to make the components of near net shape. And ceramics, we are actively working on SOFC and SOEC with a lot of components where ceramics are involved. And fuel cell technology, we have both PM fuel cells and also PM electrolyzer. But our PM electrolyzer is not just pure PM electrolyzer. We do electrochemical methanol reformation. I'll be showing that slide. And of course, lithium-ion batteries. And we also have solar energy materials where our solar areas, now we are connecting to SOEC also. I'll show one of the slides. Since the time is limited, we'll just quickly go, and then towards the end, maybe tea time also we can interact, and then my colleagues, two of my colleagues who are actually working are also going to join in 5 minutes. Next one, please. So hydrogen, this everyone knows, I don't need to show, but there are many ways to produce hydrogen. The colors are given, and you can see methane steam reforming is a gray hydrogen, and methane reforming with CO2 storage is blue hydrogen, and the target is green hydrogen. And can we think of making the top two into green? Can we make them methane into a green hydrogen without producing CO2? There are ways, maybe some of you know, and I will show you one of the slides. Actually, a company is working, and then even we are also working on that one. Next one. So these are some statistics, and then I asked my student to find who are all the people who are active, and you can see several companies who are working actually in water electrolysis. And photoelectrochemical route is another one where directly using a semiconductor electrode, you can convert light into water electrolysis and produce hydrogen. But the efficiencies are very poor because the materials, what are there existing, like titanium dioxide or any carbon nitride and all, they are not so efficient. But it will be a big breakthrough, and a lot of research groups are working. Next one. And these are some of the companies already producing at different levels of electrolyzers. Mostly you can see alkaline water electrolysis, and PM is now Eastern Electrolyser Limited, Noida is working, and then they took the technology from Sikri Karaikudi. Next one. Next. So some of the active groups who are working in India, I am talking about research groups, actively working on hydrogen production to PM is Sikri, of course, is the prime runner, and then JNTU Hyderabad and SPIC Science Foundation is also there, and ARCI, you can see ARCI we already have 0.1 to 2.5 we reached nm cube per hour. So more than this is the pure electrolysis, and now we are working on at very low voltages you can produce hydrogen using electrochemical methane reformation. And for methane reformation in conventional way with steam reforming, you need a huge systems, and when you want to convert methane to hydrogen at a system level or on site, and this is the best way, and I will show you how we do that. Next one. And Karaikudi, of course, they are the prime runners of PM electrolyzers, and you can see the stacks are at different levels. You have 6 nm cube per hour PM electrolyzer is there, demonstrated, and Eastern Electrolysers, they have taken the technology from Sikri, and at Oman also they have installed some of their systems, and now the solar powered PM electrolyzer that is for the green hydrogen production is in the process at Sikri Karaikudi. Next one. And this is what we do, that is PM based ECMR, electrochemical methanol reformer for hydrogen production. So in the conventional one, you feed H2O and then you get oxygen and hydrogen, but in the other case, along with water, you put methanol also, and then you get, instead of oxygen, you get carbon dioxide. Of course, you have to capture carbon dioxide. But the voltage, you can see, carbon-based metal can be used in stack fabric, cell voltage less than 1 volt, whereas in the conventional electrolysis with power, you need to have more than 1.23 is thermodynamic voltage, and you have to go up to 1.6, 1.6, even 2 volts, depending on the over potentials of electrodes what you use. And the hydrogen separation steps are not required like any PM electrolyzer, and easy to quick startup, and a lot of economic survey was done, and then if someone is interested in this, you can interact, and 2 of my colleagues are coming who are actually working in these systems. And now we are targeting is PM-based ECMR of 2500 liters per hour. It is a Gen 2 generation 2. We already started, and we couple with, we have used solar rooftop plants, and we demonstrate the system level of solar-powered ECMR at the moment. Next one. And yesterday, Madam Kalai Selvi, our chief guest, actually she was director of Sikri Karaikudi. And she was talking about seawater electrolysis. And of course, this is the most promising one if you can do that, and it's not so easy. So people are working on different catalysts which have high over potential for chlorine and not much for oxygen, so that, because you can see chlorine and oxygen, they're very close thermodynamic potential. So they both occur at the same potential, so chlorine is always a competing reaction. If you want to avoid that, you have to see whether you should have an electrode material which has got high over potential for chlorine selectively, or you use either the membranes, or you use other one is electroosmotic mobility and simultaneous water desalination. So these are the two generations, two strategies what Karaikudi adopts. And if you can see the left side, for OER, if you want preferentially oxygen electrolysis, oxygen evolution reaction, you need to play with electrolyzer, you need to play with the membranes and electrocatalyst, as I said, and you have to use a lot of different kinds of alloys, even whether it is super alloy or high entropy alloys now are being tested. And of course, membranes, either the membrane has to stop the remaining ions except the hydrogen ion and the water, or the other one is that it has to repel, depending on the electrostatic charge of the membrane, it has to repel the other ions, accepting only the protons. Next one. And another one is, yesterday we were talking about whether it's a PEM fuel cell or PEM electrolyzer, or now I talked electrochemical methane reformation. But the other one is high temperature electrolysis. High temperature PM fuels are known, but they have huge challenges because you need to have membranes which are stable at higher temperatures. But whether if you take SOFC or SOEC, SOFC is very well known, which operates at high temperature 700 to 800 degrees centigrade, and its electrolyte is solid electrolyte, that is yttrium stabilized zirconium. Now, if you want to operate in the reverse mode, like in PM electrolyzer, you can use SOEC, that is solid oxide electrolyzer. And you know H2E, one company, a Pune-based company, who are already doing that. You can see solid oxide electrolyzer by H2E, this company. You see in the bottom, for the same output of 1 nm cube hydrogen, the power required by PM electrolyzer is 5.3, and alkaline is 4.5, whereas you just need 3.1 kilowatt hour, including the temperature, the heating and all the costs together. So this is because, as everyone knows, as the temperature goes, because of the Arrhenius activation energy barrier, so the system process become more efficient, but you need to see where you get the heat from. Next one. So the H2E, they already have the system level demonstrations. India's first solid oxide electrolyzer developed by H2E for HPCL, IOCL, and NTPC, they already have demo systems there. With total 3 electrolyzers with a capacity of 20 kilowatt built to validate SOE technology in India, and system design developed and built by H2E. The electrolyzers have efficiency of 90% and life of 60,000 hours, which are already demonstrated in practice. And production of green hydrogen and co-electrolysis to produce syngas, these are all the other areas what they are working on. So now, I already told you that for SOEC or SOFC, you need high temperatures, and also instead of water, you need to have steam for SOEC. And if you want steam, again, you need to heat the water and then make it steam, which is again energy intensive, and then pump the steam into the fuel cell. So can we make it like green steel? Can you make green steam? Next one. So you can see this company, Horizon, Prometeo, I just downloaded yesterday when I was checking. You can see on the right side, you have the electrolyzer where H2 and O2 are written. This is the SOEC electrolyzer. And you need to have the steam from water where you can heat the water by solar thermal heating, whether it is a concentrated solar thermal heating, which is very much possible, and convert the steam. That means you are using the infrared part of the sunlight and then heating the water and then making the steam instead of making the steam by grid power or the gas fired or whatever it is. So it's a green steam that is pumped to the SOEC, and then you also need the stack to be heating at the temperature of 700 or so. So you connect to the either grid power or the solar power during the daytime and heat the stack as well as by resistive heating, and finally you make it more efficient. So that is what is the one what already is in practice, and now ARCI, we are cooperating with H2E and building a system. Next one, please. So this is the plan which we made a proposal and we submitted to DST. There is a green hydrogen production of SOEC integrated with solar thermal PV. We are already into that for a last 1 decade in the solar thermal concentrated power for the both steam and the power generation. And the project now aims at 20 kilowatt SOEC with 12 to 13 kg of H2 production and 150 kilowatt of CST, that is concentrated solar thermal system, integrated with 100 kilowatt TES, thermal energy storage, because during the night this heat can be stored with PCM based materials, that is phase change materials, in a storage tank, and then that is what the TEC. So you can see PTC, the red one in the figure. The PTC is what we have solar, that is the same thing what you see in the corner bottom, that is on the rooftop. We have this solar thermal concentrator systems, and we have also developed 1 kilowatt TES systems for a prototype, and but now the target is the one what we are going to have with 150 kilowatt CST system, which we proposed and then submitted. And both during daytime and nighttime with the TES, you operate the steam, inject into the SOEC and then run it. And we also have the solar power PVs which will heat the system, and this is what the plan, what we are going to have. And remember, please mind that it is very, very efficient system already in practice, and then with combination of solar, it is going to work much cheaper than what I projected in the previous slide when compared to PM electrolysis and alkaline electrolysis. Next one, please. So I was telling in the second slide, third slide, that can you convert, can we avoid steam reformation of methane either by CCS route or just reforming. So you produce a lot of CO2. Can we do the methane directly to carbon? And it is possible, and if you just see, some of the companies are already doing, and there is a company in Australia, they already have a prototype plants working on that. So here what you do is, you take the natural gas, and natural gas, instead of combining with steam, which is again energy intensive, and then converting into carbon dioxide and carbon, what you do is, you put iron ore as a catalyst, because iron is the best catalyst for decomposing methane into hydrogen and carbon. So what I am doing is, instead of carbon dioxide, we are making carbon which gets deposited on iron, and iron is the best catalyst to convert into graphite. So you get graphitic carbon into that, and you have to make in a fluidized bed kind of reactor, so it keep floating so that your graphite keep peeling off the iron and then taking, and you can separate with cyclones or so. So next slide, please. Next. It's not going? This is the last slide? Okay, go previous one. Okay. So this is the one, Hazard process is a company in Australia, and they are doing that one, and this is actually slide taken from them. And you have a lot of other catalysts if you want to improve, and then there are several groups working on that one. I think with this I stop, and yesterday people were talking about few more things. One is type 4 cylinders to store the hydrogen at very high pressures. If you want hydrogen to be stored at 750 bar, you cannot have type 2, type 3, you need to have type 4. So there, India, we keep importing them, and then there is no technology. And what you need is carbon fiber composites for that. And we do have carbon fibers, which are low modulus, that is T300 carbon fibers. and which are used for the rockets and all civilian sectors. But if you want strategic sectors, whether it's aerospace and all, you need T700 carbon fiber. In India, for last 2 decades, we have been working, companies including Reliance and NL, they're all working on carbon fibers, but we still have to achieve and produce, and we import tons of carbon fiber, especially for aerospace applications and space applications. Then, what we are now doing is ARCI, we are collaborating with one of our friendly countries where the technology is already available, and we are going to set up a joint demonstration for T700 carbon fibers at ARCI, and already the proposal is accepted. And once that is there, our next door advanced systems labs, they already make the composites, whether it's the resins or polymers, and this is what. So this is the roadmap, what is required, then just keep importing. Unless you make it completely indigenous or maximize the indigenous systems, you really cannot compete. And we're talking about exporting electrolyzer and exporting hydrogen, and these are all the things what is required, otherwise you cannot do that one. And we are, earlier is the better. And one more thing what I would like to say, I'm not an expert, but when I talk with some of the fertilizer companies, we closely work with fertilizer companies for some sensor application, and they say that when you want to make urea and fertilizer, NPK fertilizers, you have to have ammonia, and India imports a lot of ammonia. And ammonia is made by conventional Haber process with high temperature and high pressure. So can we make ammonia at the I think huge amount, I think 70–80% if I am right, and that much ammonia is being imported. And if you see the geopolitical situations now, unless you have Atmanirbhar, self-reliance of all these things, especially hydrogen and ammonia, hydrogen is required to make ammonia with nitrogen, and we'll be having a lot of problems. So this is one of the things, as good as defense, ammonia is also a most important factor what is in our regular life, if not just hydrogen, so that we have to work. And alternatively, what people are looking is a room temperature process of ammonia synthesis, that is electrochemical synthesis of ammonia from nitrogen and oxygen, and nitrogen and hydrogen, and that is being demonstrated at system levels already. And then since a lot of electrochemistry groups are working, both industry and academia, and I think people have to focus on electrochemical synthesis of ammonia as well. And one more thing is that there are water treatment. We have a lot of textile wastewater, and then a lot of, and wastewater treatment is one of the things what is required. And then there are a lot of technologies available, and one technology what Europe, and when I was in Japan for a long time, we were making diamond coated film electrodes, whether it's on titanium or niobium. And these mesh electrodes coated with titanium, they are dimensionally stable electrodes. Remember, if you put 10,000 boron, 10,000 ppm of boron into diamond, and diamond takes boron and becomes electrically conducting. It is as good as graphite or any glassy carbon electrode. The diamond becomes, it is black. And then you can coat by CVD or hot filament huge areas. One Condias, one company which is in Germany, they make square meters of areas of these electrodes and use for the water oxidation. That means you take this and you don't need light, you don't need any chemical, and take this in the wastewater and then electrolyze. Then what you get is at anode instead of oxygen, because you have high over potential for oxygen, you get hydroxyl radical, and within time you can just decompose and decolorize, because there are demonstration plants. So now what happens is, when you do the anodic oxidation of these waters for wastewater treatment at the cathode, always the reaction is hydrogen production. So now with the hydrogen economy, these systems will become more economic and then very attractive to the countries like India, where we have the lots of wastewater generated both from the industries as well as the domestic, and this is one of the attractive. So we need to, while we work on the known technologies, we should start, all the young people, you should start looking and reading and looking at what new technologies are available, and then maybe they are not efficient today, but with new materials and economy of scale, they definitely will become affordable. And then technologies are nation specific, because depending on your situation and your resources, your manpower, all this, it matters. So what works for another country may not be cheap and economic for us, but something else may be more cheap and then economic for us. So keep thinking, open your minds, and not just if only green electrolysis, green hydrogen means only solar and solar panels and then electrolyzer. That's okay, that we know for a long time. But can we think something out of box and then show that, so that it becomes totally innovative and totally indigenizing the technology. With this, I think I stop, and my colleagues also have enough time. Thank you so much for your attention. Any interaction we can do towards the end.